Assalamu alaikum. We will continue our lecture on carbohydrates, talking about uh, disaccharides as well as um, oligosaccharides. So the thing with disaccharides is that they are sugars that are made of two monosaccharides connected to each other. Okay, an oligosaccharide is when you have 3 to 10. So oligo means short. Okay, so a saccharide, by the way, is basically, as I said, sugar. Now, if the two monosaccharides are the exact same thing, like glucose, for example, as in maltose, we call it a homodisaccharide. Same thing with oligosaccharides. If the building blocks of oligosaccharides are exactly the same, then we call them homo-oligosaccharides. If one of them is different, then we call this molecule heterosaccharides. Now, this is basically a condensation reaction where we have linkage of two monosaccharides to each other, resulting in the release of water. So it is a condensation reaction. Now the thing is, whenever you have a polymer, a chain like nucleic acids, proteins, as well as oligosaccharides or disaccharides or polysaccharides, we call each one of them a residue. Okay, so we say a monosaccharide residue, a sugar residue, an amino acid residue, which means that it is part of a large complex of similar molecules. Okay, but if I have a single monosaccharide, then I call it just a monosaccharide. If I say a glucose residue, it means that it's part of a larger structure. Now this is an enzymatic reaction catalyzed by enzymes known as glycosyl transferases. So the link between the two monosaccharides is very stable. And once you have a reaction, a connection between two monosaccharides, the involved anomeric carbon does not rotate. It doesn't undergo mutarotation. So if it is in the alpha orientation, if the anomeric carbon is in the alpha orientation, it stays in the alpha orientation. Same thing if it is in the beta orientation. Okay, quite stable. Now, whenever you look at disaccharides, here's what you need to look at. First, you need to define and distinguish if the residues are in the D or L stereo configurations. Okay, now I'll give it to you right now. They're all in the D orientation. We're not gonna talk about a residue that is in the L configuration. Now, you need also to identify the carbons that are involved in linkage for both molecules. Sometimes it's carbon number 1 or 2, 4, 6, whatever. You need to know the order of these residues, starting with the one on the left. So the one on the left is the first one. So then the final thing is that you need to identify the orientation of the anomeric carbon for both of them, especially the carbon that is the anomeric carbon that is involved in this covalent bond. Okay, remember, whenever we are talking about a covalent bond involving an anomeric carbon, we call this bond a glycosidic bond. Okay, these are three of the most commonly used monosaccharides or disaccharides as examples. Okay, and they are sucrose, lactose, and maltose. So let's start with maltose. It's the easiest. Look at the first one right here. It's a pyranose. Okay, so it is a hexose sugar in the pyron, having a pyron ring. Now you look at it and you look at the hydroxyl group number that is linked to carbon number 2. It's going downward. Same thing with carbon number 4. The hydroxyl group is going downward. Okay, and for number 3 it's going upward. So you know that this sugar is a glucose residue. Okay, so it is a glucopyranose. Since it's involved in a linkage, we say it is glucopyranosal. Glucopyranosal. Now, look at the anomeric carbon. Is the hydroxyl group going upward or downward? It's going downward. So it is in the alpha orientation. Now, the glycosidic bond is between carbon number 1 and whatever carbon is in the second residue. Well, let's look at the second one right here. Again, it's a pyranose sugar, a hexose, 6 carbons. You look at carbon number, the hydroxyl group of carbon number 2, downward. Then this one is going upward. Then this one is going downward. So you know it is also a glucose. So it is a glucopyranose, and it is in the alpha orient. The anomeric carbon is in the alpha orientation. So and the carbon that is involved in the glycosidic bond is carbon number 4. So collectively we call this molecule alpha D glucopyranosal 1 to 4 alpha D glucopyranose, and this is maltose. This is the sugar that is present in malt, الشعير. Let's look at another one right here. So this is lactose. Lactose is made of, again, it's a disaccharide made of 2 residues. Look at the first one. It's a pyranose, a hexose. Number 2, hydroxyl group of carbon number 2 is going downward, upward for number 3. For number 4, it's going upward. So this is a galactose. So this is a galactopyranosal, and we say pyranosal because it's involved in a covalent bond. Okay. Now, is it in the alpha or beta orientation, the anomeric carbon that is? You look at carbon number 1, it's going upward. So it is in the beta orientation. So it's beta D-galactopyranosal. Look at the second one. The hydroxyl groups. Downward, upward, and it's going downward. So it is a glucose. So this is a glucopyranose. Now, the carbon that is involved in the glycosidic bond is carbon number 4. Okay, so collectively we call this molecule beta D-galactopyranosal 1,4 glucopyranose, alpha D-glucopyranose, because again the anomeric carbon hydroxyl group is going downward. Okay, now this is the structure of sucrose. Sucrose is actually a troublemaker, and we're not going to go into details of the structure, but look at this. So the first one is, again, a glucose. So it is a glucopyranosal. Is it alpha or beta? It's going downward, so it is alpha. Alpha D-glucopyranosal. Now, the second residue is a fructose. Now, the thing is, this is actually a flipped fructose. So all you need to do is actually just memorize that it is in the beta orientation. That is, the anomeric carbon is in the beta orientation. So the linkage here is basically the name alpha D glucopyranosal 1 to 2 beta D-fructopyranose. Fructofuranose. Okay, so you just need to memorize this, and you will not be questioned on such complex structure. Now notice something here. Notice that in these two disaccharides, maltose and lactose, you have a free anomeric carbon right here, which means that these two disaccharides can be involved in reduction oxidation reactions, specifically that they can reduce other molecules. So these two are reducing sugars because they have free anomeric carbons. On the other hand, if you look at sucrose, both anomeric carbons are involved in the glycosidic linkage, meaning that sucrose does not have a reducing molecule. It is not a reducing sugar. Okay, so you need to know when you can call a molecule a reducing sugar or not. So again, this is how it looks like. That's sucrose, lactose, and maltose. So maltose is made of two glucose molecules, I'm sorry. Okay, the linkage is 1 to 4. Lactose, it's made of glucose and galactose. Okay, and that's how it's linked. It's the linkage is 1 to 4. Okay, if you look at sucrose, it's made of two residues, glucose and fructose. It's 1 to 2, and it is, as I said, a non-reducing sugar. Now, these are different forms of disaccharides in here, different structures. So look at them. Look at the different structures right here. This one here is a glucose. So this is a glucopyranose. Is it in the alpha or the beta orientation? It is in the alpha orientation. Look at this one right here. What is it exactly? It is, again, a glucose residue. Is it in the alpha or beta orientation? It is also in the alpha orientation. Now, look at this molecule right here. What are these two residues? Look at them carefully. They are glucose molecules as well. But look at the glycosidic bond. It's between carbon number 1, the anomeric carbon, with carbon number 6. So the glycosidic bond is alpha, because it's going downward, alpha 1, 6. How about this one? Is it in the alpha or beta orientation? It is also in the alpha orientation. Okay, now let's look at lactose. Let's look at this form of lactose. So is this a glucose or a galactose molecule? Here we go. Carbon number 4. It's going upward, so it is galactose. So galactopyranose. This one right here is a glucose molecule because the hydroxyl group right here on carbon number 4 is going downward, so it is a glucose molecule. How about the glycosidic bond? It's 1 to 4. But notice that the galactose molecule right here is in the beta orientation because the hydroxyl group is shown that it's going upward. So the glycosidic bond is beta 1, 4. Now this is a disaccharide of two glucose molecules right here. They can be shown this way, or they can be drawn this way as well. So I'm not gonna give you tricky structures, by the way. So you look at it and you say that that's the first one, okay, and it's going in the beta orientation right here, and that is the second one, and it's also with the anomeric carbon. So, and this one right here is going upward, so this is in the alpha orientation. sorry, this is also it's going upward, so it is in the beta orientation as well. So the glycosidic bond is actually 1,4, and it is a beta 1, sorry, 1,1, 1,1. I'm sorry. So that's number one. That with number one. So it is a 1 beta 1,1 glycosidic bond. Okay. If you corrected me right away, then you're doing really well. So this is sucrose. In case you have any curiosity, if you don't care about this, then flip this slide, just to show you why it is why fructose is in the beta orientation. So it can be drawn this way, so you can enjoy the view and see how it looks like. Okay, but don't worry about the structure of fructose. Again, no tricky structures in the exam. Now the thing is, sucrose is a sugar. That's table sugar, the white sugar that we use to sweeten our drinks. Okay. What I forgot to mention is that lactose is milk sugar. Okay. So sucrose is the table sugar, and as I said, it's a disaccharide made of glucose and fructose. Now the thing is, sucrose, people try to avoid sugar because it's fattening, it's harmful to our teeth, our health in general. I believe it's really bad for our health, and I've done my best to cut down on my sugar consumption, and I'm proud of myself. Actually, you should do that too. So anyway, so the thing is that here you have sucrose, okay, and it can be modified by the addition of chloride groups at certain positions, okay, and so you have 3 chloride groups right here, and the thing is, um, this one here is actually an artificial molecule, so it is manufactured, it is not natural. It's known as sucralose, and it is an artificial sweetener, and it's the basic ingredient of this marketed product right here, Splenda, where people can put it in their drinks, hot drinks, but there are no calories because we cannot consume this molecule right here. We cannot digest it. So it doesn't add any calories to our drinks. Now, there are problems associated with milk. So milk is mainly composed of lactose. There are 2 problems that we should discuss. The first one is known as lactose intolerance. Now the thing is, in order to digest lactose, we need an enzyme known as lactase. Now, some people have deficiency in lactase, and as a result, they cannot benefit from milk. They cannot digest it. What digested instead is actually our intestinal bacteria, our flora, and that causes huge problem, because then bacteria, they would have a party actually. They would produce gas and carbon dioxide and organic acids. That results in people having problems with their stomachs, stomach ache. It can be really painful. They would have a lot of gases in their stomach as well, in their belly. That would be a problem for people around them, well, as well as themselves. And they would have bloating, انتفاخ بالبطن, and diarrhea as well. Okay? Now, as an alternative, there are some products of milk products and dairy products that do not contain lactose. Some people may take pills that would help them in digesting milk. So, but it can be a problem for children having deficiency in lactose, by the way. Now the thing is, it seems that lactase, the efficiency of the enzyme lactase, goes down with age. So people, older people might have trouble digesting milk as well, or lactose. Okay? And it does seem to be a problem with people living in the old world, that is Asia, Africa, Southern Europe. But people in the in Northern Europe, for example, they do not have as much problem as we do. Now, the other disease, is known as Galactosemia. This here is caused by a deficiency in the enzyme responsible for metabolism of galactose. So galactose would not be metabolized in our system. Instead, it can be taken into cells and it can be converted into a hydroxy sugar, galactitol. Now, this galactitol is trapped inside cells. It cannot escape cells. And its concentration increases in cells. As a result, water gets into the cells, okay? Because there's higher concentration of sugar inside the cells, so water would get into the cells. That would cause cell swelling and cell damage and death. That would result in retardation. So, and it can cause cataract as well, okay, as you can see in here. As you know, and I think it's mandatory in the US to check for deficiency in galactose metabolizing enzymes. So these are the disaccharides. So Raffinose is an oligosaccharide. It is a trisaccharide. It's made of 3 sugars. That's raffinose right here. Raffinose is found in beans, in vegetables like cabbage, maltose, Brussels, broccoli, sprouts, asparagus, and it's composed of 3 residues right here. I want you to look at them and identify each one of them. Okay. Now the thing is, we do not have the enzyme that is responsible for metabolizing raffinose. Okay. Meaning that again, intestinal bacteria would have a party, and as a result, there would be production of hydrogen, methane, as well as other gases. That's why when we eat hummus, some people, well, most of us would have trouble afterwards. Yes, I love it, but people would have trouble after eating a lot of hummus, falafel, fool, you name it, as well as malfouf, because of raffinose. So now you know. Don't you love it that you know? So finally, we have oligosaccharides. They're really, really important because they can be used as precursors for the production of drugs like antibiotics, streptomycin, erythromycin. They are made of oligosaccharides. You also have doxorubicin, which is used in chemotherapy, cancer chemotherapy. And we have digoxin as well, which is used as in treating cardiovascular diseases. Okay, so what you need to know now is basically how disaccharides are formed, as well as oligosaccharides, their significance in terms of their effect on our health and their structure.